my computer is really not behaving today very well. So hopefully my computer will not freeze as I do this. But anyway, we're going to move through a couple of these things and hopefully go pretty quick here. So anyway, so let's find out if in fact this function is continuous. So right now, if I wanted to know what I want to look at right here is what happens as I approach -2 from the left side of f of x. So as I get really, really close to -2 on the left side, if you look at that pretty critically, as I get really close to -2, what is this thing getting very, very, very close to? It's 1 over 1, so it appears to be 1. So what about the limit as x goes to -2 from the high side? What is it getting close to? So keep in mind, this is the value that goes up till -2, but not including it. And this is the other side. So what happens when I get really close to -2 on the high side? It's 1. But what happens at f of -2? What did you get? I got 1. So see, because this says if I plug in -2, that's this one. I got 1. So silly question. Is 1 equal to 1 equal to 1? Is the bridge in the same as the bridge out, the same as the bridge? So what does that firmly establish is that this graph is continuous at least up through the number +2. So then we have to kind of play that game again. So what happens at 2? What happens is I try to approach 2 from the underside. What does it get close to? Can you guys tell me? The underside of 2 would be this guy. So it looks like it's getting very, very close to the number 9, but the limit as x goes to +2 of f of x. If I come from the high side of 2, what is that getting close to? 4. So what does that tell you about it? Is it a continuous function? No, because we have a jump discontinuity. Do I even need to try to find out if the bridge matches the road in and the road out? It's pointless at this moment. We've already gotten a failure. So we have some kind of a jump discontinuity. And then what would happen then at, say, 4? Is that going to work? 4 is going to give me 16. What's 4 down here going to give me? 16. Is that going to work? That is going to work. So we would be able to kind of polish that up and say the limit as I approach 4 from the left. Oh, that was mean. Is the limit as I approach 4 from the right. So is it continuous? Read carefully. Dang it, somebody stole the bridge. Why am I saying somebody stole the bridge? Oh, x equals 4 itself doesn't even exist. So what does that tell you about that spot on the graph from last year? That's a removable. It kind of comes in and road out work, but this is not the same as g of 4 because it's not even in the domain. So we kind of talk about that a little bit. So anyway, continuity on an interval, a function is continuous on an interval if and only if. Now in more advanced math classes, you'll see this little thing that says IFF. IFF is really a strong statement. That means if and only if. That means you can read the statement forwards and you can read the statement backwards. So this is kind of an interesting thing. Like if you were to go back to your days in geometry, you see those two angles right there? You guys remember those called corresponding angles? So in parallel lines cut by a transversal, corresponding angles, I'll say it this way. Corresponding angles are congruent if and only if the lines are parallel. So that means if the lines are parallel, the angles match. But if the angles match, what does that make? It means the lines would have to be parallel to make it. It kind of goes both ways. It's a very, very strong statement. So it is continuous if and only if it is continuous for every point on that. So in other words, I can't call it continuous if there's something that went wrong. but that means if nothing went wrong, what would that tell you? That it was continuous. So if you know it's continuous, you get to say that all the points are good. But if you know all the points are good, you know it's continuous. Now, when we talk about an open interval, it's kind of silly how that works. It's just notice it's continuous on that open interval. It's the same kind of definition, because sometimes we have open intervals and sometimes we have closed intervals, and we'll have to talk a little bit more about that as time goes on. So I'm not going to do too much about this because it's a pretty simple little concept. A function is continuous on the closed for the same thing, but notice on the closed interval, it is continuous on the open interval, and these things happen where if you try to come at it from one side, it's the same as hitting the point, and as if you try to come at it from the other, because keep in mind, on the interval AB, if this is the only place where it is done, notice as I try to approach A, you see the plus? Why is it saying plus? Because it's from the right side, and I'm not even allowed to approach from the left side, because what is it saying? It's saying that the left side doesn't even exist, right? So on a closed interval, you would actually have to say it's all continuous, but not only that, as you approach that endpoint, it actually tags that exact same endpoint. So that's not that big of a deal. So this is obviously a graph that has some discontinuities. You can see we have a removable discontinuity at 1, and we have a jump discontinuity at 2. So what I could say is that this graph is continuous on. I do have to say I don't like the way this looks, because that's like a half open, half closed situation. Where else is it continuous? On 1, 2, you can have half open, half closed. And where else is it continuous? On 2, 3. And so that is a little bit strange that we're saying it that way, but if I say if it's continuous on 2, 3, that means I can get any point between 2 and 3, but not only can I do that, 3 itself matches what happens as I approach 3. Now, when we look at these things, I tried to do this a little bit with you guys last year in terms of looking at continuity. Did we talk about polynomials last year? What created discontinuities for us? Is one was piecewise functions. What else created discontinuities? Vertical asymptotes, which means you had a rational equation that had x's in the bottom, right? By the way,
Dividing by 0.
polynomials never have x's in the bottom. They can't. In fact, polynomials have nothing but whole number, nice, pretty exponents. And as soon as you put a variable in the bottom, you made it negative. Now, Gian, you said what?
Dividing by 0.
Dividing by 0, yeah. Is there anything else that created discontinuities last year? Well, removable, but that again comes from that 0 in that bottom. That's going to force something down there.
Square roots.
Square roots, that's it. So when you look at it, polynomials are going to be continuous for all reals, aren't they? Those are never going to have any kind of thing, any kind of issue with it. Now, I will say this one is kind of funky. Rational functions are continuous on their domain. I hate the way we say that. It feels like everything should be continuous on its domain. See, because when you look at it, it begs the question, but if you have a problem with an asymptote, say at 2, would you guys call that a continuous function? Well, for me, I feel like
on its domain.
But it is continuous from negative infinity to 2 and continuous from 2 to infinity. See, I could say it's continuous on those open intervals, but I feel like that kind of begs the question, isn't everything going to be continuous on its domain? I mean, last year we kept listing domains, didn't we? Everything's going to be continuous on if you break it up in those things. So anyway, that's not that big of a deal. I just don't like it too much. So given this thing, what do you guys think about sine of x squared? What can I take the sine of? Can I take the sine of anything I want? Is it going to matter if I square it and then take a sine? So what am I going to say is it's going to be continuous on negative infinity to infinity, or in other words, for all reals. Now, I will say this one is going to be a little bit jacked up, because if you look at the cosine, plus 1, it's going to look about like this. It's going to go as high as 2, come down and like this, like that. You guys okay there? What's going to happen then when I try to take the log of that? What can you take the log of? You can only take the log of positive numbers. Can you take the log of 0 itself? If you try it, what happens if I say, hey, calculator, I want to know what is the log of 0? It says, I don't think so. So is this problem going to be continuous? No, in fact, it's going to die here at pi. Where else would it die? Well, this is 0, here's pi, here would be 2 pi, this would be 3 pi. See, it's the standard little thing, but every time it dips down and hits 0, it's going to break, isn't it? So how the heck could we say it? Well, in my opinion, I'm going to go ahead and pull this thing back to here, and I'm going to say it's continuous on negative pi till positive pi. See, now, notice that's an open interval. Why did I not include negative pi or positive pi? Because those were bad. But doesn't this little block of information keep repeating itself forever? Ah, so if we did a plus 2 pi k, I could say that all of those things are, as long as I don't pick those endpoints where k was some element of the integers. So I have an infinitely discontinuous function, but I have mainly good spots. Now, I'm actually kind of curious what the heck that thing looks like. So let's take a look at it.
I did graph it, and it does look really cool.
It does look cool. It's
for a function.
Worth a look. So let me see if I can give it a quick look in Desmos. So I don't know if you guys can all see that, but I'm going to go ahead and give myself a new window because I don't want to destroy what I have there. But I have a natural log. This is weird. The natural log of 1 plus the cosine of x. Oh. It looks like a fence, like one of those wire fences that somebody puts on their yard. Do you see the infinite discontinuities that are happening? Every time we get close to some multiple of pi, right in here. Now you can see it's jacked up, but the resolution is not great. But are these asymptotes, or are they connected? Those are asymptotes. It just have a little bit of an issue with the resolution there. So moving along, let's go down a little bit further. Let's go back to this. All right. So again, this kind of gets back to the intermediate value theorem. What I told you is that if a function goes from A to B and it has some height, it's going to have to go through every intermediary height along the way. Now, what a lot of people think when I gave that example from 3 to 10, could it have gone through -1 on its way from 3 to 10? I mean, think about it.
Yes.
It can. So if you have a height of 3 and a height of 10, and it started over here, could it get there? Well, yeah, it might have dipped down and then come back up. See, there's nothing that says, so if I said, hey, will it ever hit -1? The answer is, I don't know. I can't really make any kind of determination. Will it ever hit 9? That I know, as long as it is continuous. So skipping along in here a little bit, if you measure the outdoor temperature, now one of the things about temperatures is should those be continuous? Those have to be continuous. So on the porch, it was 47 degrees Fahrenheit. I only wish. 47 degrees Fahrenheit at 8:15. You know what it was at 8:15 this morning? No, it was not 70. Keep going. the overnight low this morning was 81 at like 4 o'clock in the morning. So by 8:15, it was probably 87 already. It's getting warm. Yeah, it's kind of freakish how warm it feels. But anyway, then if you measure the temperature 4 hours later at 62, explain why there must be a time where it's 51. Well, is that pretty obvious? If it's a continuous function, does there have to be some moment in time that it passed between 47 and 62 when it hit this weird number? I mean, obviously it has to hit that number because it's in the middle. You can write something out. I don't really particularly care. So piecewise, determine if the intermediate value theorem applies. Now, one of the things that's important is when does the IVT apply? It only applies if the function is continuous. So the question is it continuous on this interval? So please understand it never in this thing says to find all the answers. It just says, does it apply in this situation? So look right in here. What happens is I try to get close to -2. I would get some value, I guess that's +4 and 1 makes 5, right? Which is, how about as I approach x goes to -2 from the high side, -2 squared, I would get 5 again. So it appears to be functioning perfectly fine all the way throughout from -4 to -2. Actually, this is true. Now, why is it true? Because everything from -4 to -2 only deals with this thing right here. But what does -3 to 0 do is it takes a little bit of this region and a little bit of this region. So is this itself continuous by itself? If you looked at that graph, it would be great. Is this one by itself continuous? Yes, it's a polynomial. What's the only place it could go wrong is the little spot where they got stitched together. Did the stitching work? So does the intermediate value theorem apply? Yes, it does. This is again true. The intermediate value theorem applies. How about from -1 to 1? Well, look right in here. Is it going to apply from -1 to 1? Careful. What did they do that screwed up is the 1 is actually not part of this dude, it's part of that dude. Did it work? What happens as I approach 1 here? Is I get 2. What happens as I approach 1 on this one? So what we could say is that the limit as x goes to 1 from the left side of f of x is not equal to f of 1. See, I'm trying to actually honor the definition because it said if it is true on a closed interval, it not only has to be true on the interval, it has to match that endpoint. How about 1 to 4.5? Do I need to consider the jump here? So this is going to be fine. So what happens is I get really close to 4. I would get 6 here. As I get close to 4, what do I get here? 6. Is that going to be okay? Yes, it is. This is going to be true. They're each on their own interval correct, but then we can also check the endpoints as well. And then how about from 2 to 7? What's wrong with from 2 to 7? What's going to happen as you go from 2 to 7? What are we going to pass that's going to be a problem for us? It's going to have a problem at 5. The answer is no, because x equals 5 is discontinuous. Okay? So now does that mean we can't do stuff on the graph? No, but you cannot say, oh, I've got this graph, and it was below the axis over here, it was above the axis over here. It had to have hit the axis. Why can I not say that? Because have you ever seen a graph that does this? So can I say it was below, now it's above, it had to cross the axis? No, that doesn't apply anymore. Why? Because it was not continuous. It had a pretty substantial break, didn't it? And so moving to the back side, like I said, I'm trying to go fairly quickly through this, but I think it's a simple concept. So we can use it to prove the existence of a value, but we have to know that it actually applies first. So the velocity of a particle moving along a line. Now this is kind of a strange concept for a lot of you guys when you first show up in calculus, but we will do a huge number of problems later on called particle motion. So have you guys ever seen an air track like in a physics class where they put a little thing on it and it just moves back and forth on it? Some of you guys maybe have it. Can you visualize that? Like you have air going on it, so there's not much friction, and you could actually study how fast or how slow the little car is moving along the track, if you can kind of picture that. But what's happening, though, is the car is moving along the track this way. What's it not going to do then? It's not going to go up and down. So when we talk about this idea of particle moving horizontally on the x-axis, we could actually do the same thing as when we talk about like throwing a pen, just tip it on its side. I'm ignoring side-to-side motion. I'm only talking about straight up and straight down. So we're kind of talking about a one-dimensional graph. So the velocity of this continuous function, where t is measured in seconds and v is in feet per second, why would you be able to say that somewhere it had to be at rest? See right there? Since v of 2 equals negative 5.5 and v of 5 equals 2, it's a continuous function. What would you know? So there must exist some t on 2 to 5. You follow that? It couldn't be at 2, it couldn't be at 5, because we already know what the answers were at 2 and 5. Where what would be true? V of t would be 0. Now what would that mean? Think about why someone would want to know that information. What does it mean if V of t is 0? It stopped. In particle motion, it's something that we always want to know. Where did the dumb thing just stop moving? Even if it's just momentarily. So obviously in the pen throw, when did it stop moving? When it hit the top and started falling back down. Show that there is a positive real solution to this one. Well, again, a positive real solution to that is kind of interesting. So if we were to set this like, dang it, be a little bit careful with your pluses and minuses here. Okay, so what about if I decided to pick 0 itself? So if this is my function, what is f of 0, everybody? It is negative 2. So let me ask you a question. What is f of positive 2? 32 minus 2 minus 2, I think 28. Is this a continuous function for starters? It's a polynomial, isn't it? So at 0, I got negative 2. At 2, I got positive 28. What can you then conclude? Did it have to cross in there somewhere? Oh, okay. So by the intermediate value theorem, there must be some value x where f of x equals 0 on the interval from 0 to 2. Now, it could have been a different interval. I might have made it a little bit wider. What if I tried the number 1? By the way, 1 also gives me negative 2. So I could have used that as my starting value either. I just needed a little bit of something here. And the last little piece is we've got these two functions, f and g. The functions f and g are continuous. And the table gives all these values. The function h is somehow like this. Explain why there's some value where h of r would be negative 5. So I got to think about this one a little bit. Somewhere from 1 to 3. So let's see. What is h of 1? let's find out what is h of 1. Now, h of 1 is f of g of 1 minus 6. So let's see if we can figure out what that is. What is f of g of 1? Let's see, g of 1 right here is 2, isn't it? But what was f of 2? 9. And 9 minus 6 is 3. So what I just found out is that h of 1 is identically 3. So, like, isn't that weird? We got some weird composite function, but we can talk about that composite. So what about h of 3? Which is f of g of 3 minus 6. Okay, what happened there? Well, f of g of, that is strange, because if we did this, f of g of 3, so g of 3 was 4. Didn't like that for a second, but I was looking at the wrong function. F of 4 was negative 1 minus 6, which is negative 7. So would it be true that if it went from 3 to negative 7, that somewhere in that journey, it would have to cross through negative 5? Isn't that kind of weird? Yeah. So does the intermediate value theorem apply? Yeah, because that's in that interval. So explain while there must, by the IVT, since negative, I'm just going to say negative 7 is less than negative 5 is less than 3, there must be some value on the interval 1, 3 where h of r must be negative 5, because that is quite clearly sandwiched between those values. So anyway, intermediate value theorem, I don't think it's that big of a deal, but quite frequently it can be a big deal. It's kind of like the squeeze theorem, talking about something you can't touch by relating it to something that you can touch. So that was a pretty quick little lesson. So I'm going to give you guys some time to work on the little packet that was on the intermediate value theorem for a few minutes. And then probably 20 minutes or so, I'll pass out the take-home test. For those of you guys at home, I will also